So you wanted me to correct number 28 for 6-3.
Yes. 28.
And I'm just sort of.
Okay, so let's just take a second and remember what this thing is. It's a difference quotient, which means we're trying to find the slope at some point. So we have
Hold up. What?
This thing that we have is a difference quotient, the f of x plus 8.
Oh. Yeah.
We talked about this before, minus f of x all over h. That's the context here. And we're trying to evaluate what that is. Because what this is we're given some function, f, and we want to know here at this point, what is the slope right there? And so we say, well, at that point, if we call it x, what we could do is go some distance beyond it. We go here to this point, x plus h, so that this distance from here to here is h. If we plug in x plus h, he really wants his cheese. Give me just a second. Give me just a second. I'll just give you the whole thing. Here's your cheese, buddy. There you go. You're welcome. So if we go some distance beyond it, a small distance, a distance of h, and we go to whatever number that is, and we plug that into our function, we get some output. Let's see what that output is. It's whatever you get when you plug that number into x. That's f plus h. Sorry, when you plug that number, x plus h, into the function f, that's your output right there. Then when you plug in this number, x, you get a different output, which is, well, it's whatever you get out, which is f of x right there. And so then the slope we can estimate the slope by saying, well, it's the rise over the run. And the rise is the difference between f of x plus h, which is whatever that is, of x plus h, minus whatever that output is right there, f of x. That's the rise. The run is this distance from here to here, which we could call it x plus h minus x, but I kind of already said, well, look at that. We went over a distance of h when you do this, or x, it's the opposite of what I wanted to do there. We could say f or x plus h minus x is the same thing as just plain old h. That distance is h, and that is what this is. It's a difference quotient. So that's the context for this problem. We have some kind of function, and we're trying to estimate its slope at a given point. Okay, so you following me thus far? Is your mind refreshed on why the hell they gave you a question like this? Like, what does this even mean, and why am I plugging these crazy symbols into these other crazy symbols? This is what's going on.
This is the thing that we did in that calculus section, right?
Precisely. This is the beginning of calculus right here.
Great.
Right. So are we good to go? Are we good to go? Now we have the motivation for why this problem exists. And this is what we're doing. Okay. So with that in mind, we could say, well, when that function f is given to you, which they say we have a formula for it, and it's x divided by 1 plus x. And so we're going to imagine that I plugged this into my calculator, my graphing calculator, and it gave me this picture right here, and that's what that thing is. And now what we want to do is say, well, at any given x, what is its slope? And that's why we're doing this thing right here. And so that's what we got to do. So what I'm going to do is with these two things here, in fact, I'm going to go ahead and erase the picture I drew right here. You got this picture down? At least in your head. Let's keep this in mind. That's what we're doing here. That's the motivation. Now what I'm going to do is say, okay, this thing right here, I'm going to go ahead and rewrite it right here. F of x plus h minus f of x all over h. The rise over the run. All I'm going to do is just manipulate symbols right now. I'm going to say f of x plus h is what I get when instead of plugging an x in here, I plug in x plus h. And so whatever goes in here, I have to replace here and here. And in this case, it's x plus h. And in this case, it's x plus h. And so I'm going to replace this symbol. In other words, this is the output. This is how you get the output. This tells you if, for instance, I said, we're going to plug in a 5 and I wanted to draw this thing and I'm here at 5, I would say, well, f of 5 says to take 5 and divide by 1 plus 5, 5/6. And so I would have my height right here, which would be 5/6. So that's what I've done. And going back to the original picture, right? I found my height. That's what I'm doing here. And it just happens to look kind of funky because we're doing something abstract here, right? We're saying go to some point and then go to some point beyond it, which is some number and blah, 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 blah. But that's why it looks funky. But again, this output right here, well, that is exactly what this is. That's the height above the x-axis right here. And so that's the height I'm going to use right here and say, okay, f of x plus h is this thing right here, x plus h over 1 plus x plus h. Okay, now I'm going to subtract off what? Well, f of x. So when I plug in an x, I plug in my x right here, and I plug in my x right here. And again, if this were, say, 4, I would say, okay, f of 4 is 4 over 1 plus 4, or 4/5. And so then I would be here at 4. I plug in a, say, a 4/5, and there you go. And now, when I subtract these two things from each other, which is what I'm about to do, I will get my rise in the numerator, which is what I'm doing right now. I'm going to take this number, whatever it happens to be, that output right there, plug him into the formula, x over 1 plus x. And now the run, of course, is h. That's how it's set up. That's what we do here. And so now, okay, I'm going to get rid of this, and I'm going to get rid of this, and we're pretty much done with f right now. As far as I can see it, this was my goal, was to calculate this guy right here. And I've already plugged in the value, so I don't need this anymore. I'm just going to make some room. So, okay. Now, okay, I'm looking at this. I'm seeing fractions inside of fractions. And I think I know how to, what I want to do, this is one of the things we're going to talk about today. Basically, when I see that, I know, okay, I need to kill these guys because I need to turn this into, you know, this is everything you've been doing in this section, right? Like, so what I'm going to do is think about this. Myself a bit more room, actually. Give me just a second. I'm going to rewrite this. X plus h over 1 plus x plus h minus x over 1 plus x all over h. So I have fractions inside of a larger fraction. So from our conversation last time, I know what I'm doing. I'm going to kill those fractions by multiplying both the numerator and the denominator by the same thing, right? You following with that? That's what we did. Okay. Okay, so what do I need to multiply by?
Wait. On your second fraction up top, shouldn't it be 1 plus x?
Yes. Thank you. Excellent. Great catch. Okay. So what am I multiplying by?
1 plus.
So let's be a little bit abstract here and look at the overall picture looks like this. I have A over B minus C over D all over something. We're not really worried about that because there's not a fraction down there. If I had this, what would I multiply by to kill that guy and to kill that guy?
B and D.
B and D. I would say I'd have to, in order to kill that guy, I gotta multiply him by B. In order to kill that guy, I gotta multiply it by D. And so that's what I would do. So in this case, it's no different. I have something in the denominator here. It's different from this something in the denominator here. And so in order to kill both of them, I gotta multiply by both this guy and this guy right here. So what am I multiplying by? You tell me.
1 plus X plus H.
That's one of them. And I'm going to go ahead and do that in parentheses like this.
I have a question though.
Uh-huh.
I thought you only had to multiply by 1 plus X plus H because the second denominator has 1 plus X in it already.
Well, no, because let's look at this. If we have, well, so if I did, I would have 1 plus X plus H in the numerator, and I would have 1 plus X in the denominator. Those things do not cancel out.
Oh.
Right? It's subtle. It's really subtle here, but that does not cancel that thing. Those are completely different things. So if what I'm saying here is what I'm drawing here,
Right, okay.
This guy, if I went and multiplied him into there, yes, clearly this first one here will kill that first denominator. But now in the second fraction here, we'll have this over this. And it's like, well, this is not the same thing as this, right? And we could see that by actually, like, if you want, we could plug in some values, right? Like, let's say that X is 2 and H is 1. We'll have 1 plus 2 plus 1 in the top, and in the bottom, we'll have 1 plus 2. That is a 4, and that's a 3. Those guys in general do not cancel.
Right, okay.
So that's, yeah. This is tricky stuff. This is why it's a challenge problem, because, yeah. So, okay. Different denominators. We killed the first denominator with that guy. What do I need for the second denominator?
1 plus X.
1 plus X. So I got to do that in the top and the bottom. So now let's just imagine that these two have jumped over and hit the top thing. What cancels out and what's left over?
Okay. For the first denominator, 1 plus X plus H cancels.
Yep.
And you're just left over with X plus H, right?
X plus H and
1. Wait, what? Hold up.
this guy too.
Oh, I forgot about that one.
Yeah, we're bringing both of these guys in.
Right. And then
in
1
the
plus X.
numerator. And just, I'm going to be real explicit here because this is what it looks like. Once he jumps over, this is what that first fraction looks like. There's only one cancellation, is the 1 plus X plus H in the top and the bottom. And then that guy comes along for the ride. And so he will show up right here. Okay. Now I'm going to put a minus sign because that's that minus sign right there. Now this guy has jumped over, and what am I left over with? What cancels and what am I left over with?
The 1 plus X cancels, and you have 1 plus X plus H times X.
Okay, so I'm just going to write it like this. Okay, now the denominator, well, this is kind of nice because there's no additions here. It's just H. So I could just write this as H times that thing times that thing. In fact, I'm just going to copy this down almost exactly and say that's the same thing. It's H. Oh, excuse me. 1 plus X plus H, 1 plus X. Okay. So moving on now. where do you want to go from here?
Now can you start canceling?
Well, can we? I mean, if anything cancels, it's going to be either a 1 plus x or a 1 plus x plus h or an h. And here, well, I have 1 plus x, but not over here. I can't factor it out and cancel it.
All right.
Here I have this guy, but I can't cancel him with that because he's not here. I can't factor it out. So we're at a point now, we're kind of at a deadlock. And where do we go from here?
Would you do the would you simplify everything, I guess?
Yeah, or complicate it, depending on how you want to think about it. What I'm going to do is multiply out that numerator.
Right.
And I'm going to hold off on multiplying out the denominator because maybe and hopefully something's going to cancel. That's usually the way I deal with it. I'm going to just do one step at a time. Maybe if I multiply this stuff out, something's going to cancel out, and then I'll be able to cancel the top and the bottom. So I'm going to go ahead and multiply that first guy out. First outer, inner, last gives me x. Outer gives me 2x's is x squared. Inner is just 1h. The last is hx, so plus hx. Okay, now I'm just going to write this guy by taking a negative x and distributing it into each one of these. So the negative x times 1 gives me minus x. Negative x times x gives me minus x squared. The negative x times h gives me minus hx. And my intuition was pretty good. I could see that we are going to get some cancellation. And just so you know, in the future, when you're doing 1,000 of these for homework, right, which you will do in Calculus 1, there's almost always going to be some nifty cancellation that goes on right here. Something is going to subtract off. Like you'll notice we have an x squared minus an x squared. We have an x, oh, minus an x. We have an hx, oh, minus an hx. That almost always happens. And so when you get to this point, when you plug something into a difference quotient, at this point, you almost always want to try to do some cancellation like this. Sometimes you'll be able to factor one of these guys out and cancel it or something, but in general, you'll want to do some kind of multiplication and then do your canceling. And so what am I left with on the top in the numerator?
Pretty sure it's just h.
It's just h. And let me double check that. We have a plus x minus x is gone. Plus x squared minus x squared is gone. Plus hx minus hx is gone. All I'm left with is one positive h. So I'm going to copy the denominator down exactly. And now I'm glad I didn't go and multiply that whole denominator out. I've made that mistake so many times in my life where I'm like, well, I'll just multiply everything out. And then I get to this point and I'm like, well, I didn't need to do that in the bottom. You know, and so just one step at a time, right? I'm just, and in this case, it worked out to my benefit. That'll work 9 times out of 10 to your benefit. And so what cancels and what's left over?
The h's cancel.
Just cancel. And now I have what?
You have 1 over 1 plus x plus h times 1 plus x. I think.
1 plus x. And that is the answer right there. Now in calculus, what we do is, remember the whole point was this, was that we had some function, did something like this, and we are trying to estimate the slope right here at x. And we can't, what we want to do is take a very, very, very small value of h, because we want to let h, basically, it's called, we want to let h go to 0. And the problem here is, if you remember, I can't just plug in a 0 right here. And so whenever you're working with these, it's like, if I can cancel that h out of the denominator, then hopefully you can. And once you get to a point where that guy cancels out, you could say, oh, I can plug in this guy. I could plug in a 0 for h. And so this is the answer that we're looking for right there. But now we could take that next step, which you're going to do in calculus, which is, now do we have a problem with letting h go to 0? Well, no, let's see what happens. If h goes to 0, then this thing goes to 1 over 1 plus x plus 0 times 1 plus x. 1 plus x plus 0 is just 1 plus x. And I don't have that pesky problem of having a 0 in my denominator, which means junk. Now I can substitute h equals 0, and I get 1 over 1 plus x, that quantity squared right there. Or we could leave it like this, that's fine. It's the same thing. And then what we have here, and this should be a negative. Why isn't this a negative? 1 plus h. Oh man, this is going to drive me crazy. Why is this not a negative number? Oh my goodness. This should be a -1 on top.
Why should it be negative?
What?
Why should it be negative?
Because I know what this function looks like, and it should be a negative number. Give me a second. What did we do with it? It was x over 1 plus x, x plus h over 1 plus x plus h. Yeah, and then we did that to kill that. That gave us that. That gave us that. Whoa. Okay, I'm gonna have to puzzle over this for a while, but we're gonna drop it right now. I'm sorry. And that would be what the slope looks like at any given point x. So this is where you're going in calculus. This is the whole point of calculus right here, is to get this function. Given a certain function, you're trying to get what's called the derivative, or in your book, it called it the slope function from it. Hey, buddy. Hey, hug. Hugs. Oh, I love you. Mwah. Really bugs me. It's not negative. I don't know what we did. Maybe I'll look back over this later. Doesn't matter. That's the point. This is what you're looking for right there. Does that make sense?
Yeah.
Aside from my crazy negative that should be somewhere, and just forget it. Forget all about that. But this is the idea, and you're going to see this a lot this difference quotient will be all you eat, breathe, and sleep when you first start calculus. But then what's cool is you're going to learn nifty little tricks so that you never have to use it again.
Fantastic.
Yeah. But it's good to know what you're doing. Like, that is the whole point of calculus, is like, we need the slope of a curvy function at a point, but a curve doesn't have a slope at a point, so we have to do this nifty little go past the point that you care about and then shrink that point to 0, but you can't just plug in a 0, so hopefully something will cancel with that h in the denominator, and that's the name of the game for your first couple weeks of calculus. So, okay, any other questions with this?
Not with this problem.
Oh, I mean, okay, so what else do we have questions with?
The challenge problems that you gave me for today.
Oh, okay. Let's look. Oh yeah, those were difficult. I figured we'd be doing that. So number 31, find k so that this thing divided by that has remainder 0. So it says that we're taking x cubed minus kx squared, x cubed, give us a little bit more. X cubed minus kx squared plus 3x plus 7k. Did I get that down right?
Yes.
We're taking that and we are dividing it by x plus 2. And it says find the value of k so that the remainder is 0. So what I know from this is if I just plug in with my algorithm, right, and doing the thing that we talked about last time, eventually I'll work down to where I get a remainder.
Uh-huh.
And then the idea is, well, we want that remainder to be 0. So maybe, and I'm not sure yet, like this is just my intuition on this problem. I'm thinking maybe if we just plug and chug without really using our brains and just do the algorithm, I'll be left with some expression. And then, for the remainder, the very last thing that I get. And then maybe I could set that thing equal to 0. That is what this is saying, is like find a value of k. But again, I'm not 100% sure really what that means as of right now, but I'm hoping that what I'm going to end up with is something that only has a k in it. Maybe it'll be something like 2k plus 1 will be my remainder. If that's the case, I do all this stuff and I end up with 2k plus 1 is my remainder. I could say, well, if I set that equal to 0, let's just see, I could say, well, then 2k equals -1, k equals -1/2. Then this hopefully will work out so that I'll do all this stuff and I'll end up with some expression like this. I'll set it equal to 0 and say, well, if k happens to be -1/2, then if I went through and did all this stuff, in the end, my remainder would be 0. So that's what we're going to do. But I don't know. That's just my intuition. I'm hoping that that's going to happen. I'm not sure if that's going to happen, but let's just plug and play and see what happens. So what am I doing with this? You tell me what we're doing. Long division, so I need to write something right here. What do I need to write right there?
X squared.
Yes, because if I take x squared and multiply it by x, I get this number right there, which is x cubed. So x squared times x is x cubed. Then I got to distribute him in, and I should get x squared times 2 gives me what?
2x squared.
Plus 2x squared. Now I'm going to take that and subtract it off. The x cubed and the x cubed are gone. And now I have, well, whatever minus k is, minus 2, right? So minus k minus 2, whatever number that is. I don't know what number that is, but if that were like a -3 and I did a -2, then I'd end up with a -5. And so I'm imagining this number right here is just some number. Does that make sense what I just did there?
Yeah.
Yeah, and so I'm just treating that whatever this k is, I don't know what it is. But if I did, this is what I would write right here. Because if it were a -3, and then I took and I minused off a 2, I would have a -5. And right here, I would just write a -5. So that's what I'm going to do. And then I said in the hints that it will make your life a little bit easier to rewrite this as a negative k plus 2, but we didn't need to do that. You want to do it like this, or like with the minus 2? Let's just do it like this. Okay, so I did this. I have this number. Again, it's like, oh, there's your -5 or whatever it is. Okay, now I'm going to drop these guys down. Plus 3x plus 7k. Okay, now what number do I have to put here? In other words, I'm going to write a number here. And when I multiply it by this thing, it needs to be this.
So you'd have a minus k plus 2 times x.
There you go, minus k plus 2 times x. And now, and as I do this, once I write that up, I'm looking at the overall picture and saying, well, hold up. We have x cubed, x squared, x, and then no power of x. We have something in terms of x and then no power of x. So as I do this, I should end up with something that should be x to the second power, x to the first power, x to no power. So this is looking good. I feel good about this. So I'm going to go ahead and do my little trick here. Okay. Take this and multiply it by this guy. And what do I get?
Minus k plus 2x squared times x squared, I guess.
Minus k plus 2x squared, which is exactly what we should get. So now I feel good that I did indeed write the correct thing up there. So now he distributes into here. And what do we have?
Minus 2
Minus
k.
K plus 2, right?
And then an x on the outside.
And then one x on the outside. Yeah, right? Because again, I'm just thinking about this as a number. If that were just a 5, right, I would say, well, this would be minus, right, whatever 2 times 5 is. Since we don't know what that is, I'm just going to keep it like that. No reason to multiply this guy out or anything. I'm just going to write him like this. K plus 2 times x, like that. Just going to double check. Yeah, take that guy, multiply him there. It'll be a minus. Yes. 2, yes. K plus 2x, K plus 2x. That looks good. Okay. So now I'm going to take that and subtract it off. That guy kills that guy as well. He should. And so now what do I have when I do those guys? What's left over?
Minus 2. Oh boy.
Yeah, so this is just a number. Is this going to be minus or plus right here?
That's going to be plus.
It's going to be plus because we're minusing a minus. So you have, so in other words, we're taking one number plus another number. Let's just write that. What would that be? What's that first number?
3x.
Yeah.
Wait, no.
I'm going to forget about, but again, if this were, say, 7x plus 2x, I would just say, well, what's 7 plus 2, right? We would do the coefficient first. And so what I'm saying is, let's just figure out that coefficient, and I know that that x is going to come out here at the end, right? And so what is this plus that?
5.
No.
Well, because you're making it a positive 2, right?
Positive 2. But
right.
But it's not 3 plus 2. It's 3 plus whatever this is. It's 3 plus 2, k plus 2. That's my coefficient. So, like for instance, if it were 3 plus, if k plus 2 were 5, we would have 3 plus 2 times 5, or 3 plus 10 or whatever. Yeah, but we don't know what that is.
Okay.
So right now, yeah, and so that's the idea, right? I'm just going to add those coefficients together right now and say, well, that is what I would end up with. And in fact, I'm going to put a little bracket around it so that I don't mess that up any further. Just like that. Now I'm going to drop the 7k. Okay. So that's my coefficient, whatever it happens to be. Now, what do I need to put up there?
What do you do? Plus 3 plus 2 times k plus 2.
Yep. There we go. And then so there's that final number right there is all of that stuff. 3 plus 2 times k plus 2. Just like that. And so now, just like you said, when I take that, multiply him by there, I do get the very thing that's going to kill that, right? that times that is that 3 plus 2 times k plus 2, whatever he happens to be, times x. So there's x. And then it's just whatever number that is times 2 right there. And so, like, again, if that were a 7, I would just say, well, that's 7 times 2. So this thing, that whole bit, 3 plus 2 times k plus 2, blah, 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 comes down and hits the 2. And so now I have 2 times all that stuff right there, which is 3 plus 2 times k plus 2, like that.
Oh boy.
Oh boy. But now we're almost done. And so, okay, finally, subtract that guy off, right? And this and that cancel. Yep, they sure do. Okay, they're gone. Now what do I have?
Yeah, you have 7 minus, yeah, minus 2, right?
Yeah, and this is my intuition. This is where it's really tricky, because before we were saying, well, just do the coefficients first, and then we'll leave the x's at the end. This is not the same situation. In this situation, this is not a, k is not a variable. K is some number. It is a specific number. And so whatever this is, that's just 7k minus all of this stuff right here. Like that. Now, if, and let's look at the difference here. Notice that this was, in this case where we did it earlier, it was one number times x. This was one number times x. And so we could just say, well, just do the operation with the coefficients, and then you have it, and we'll just leave the x on the outside. That's fine. It's like saying 7 apples minus 3 apples is 4 apples. And so we could do that. In this case, you have 7 k's. Oh, but that's not something times k. The k is like buried in there. And so we can't just say, well, it'll be 7 and then whatever that is, and then the k's will be on the outside, because the k is not on the outside there. Does that make sense?
Mm-hmm.
Yeah, so just to be clear, if in the very end we ended up with something like this, and then minus 2 plus 3 times 5, and then with a k, right? If they both had k's on the outside, in the same way that these both had x's on the very outside, then we could just do our deal with the coefficients here, leaving the x on the outside. We could do that with the k's. But in this case, since the k is buried inside there, we're going to have to simplify this another way. And the most straightforward way is to just say, well, it's whatever this number is, boom, that's the 7k, minus whatever that big number is right there, which is that guy. Now, as I look at this, I could say, well, my division algorithm is done because I started with something cubed, I divided by something to the first power, and I ended up with something that was x squared, x to the first, x to the 0. I don't have any x's in here. And so now the very last thing is going to be my remainder. Another way of looking at it is saying, well, my remainder no longer has an x in it, or what this thing that I'm working on now no longer has a value of x. So in my head, I'm thinking, oh, that's just a number. If I plug some value of k in there, maybe it comes out to be 11. And so in my division algorithm, I would have just some number. And so I would say, well, my algorithm's done. I am done with the division, and now I have a remainder. And so I'll put whatever that remainder is over x plus 2. Okay, that is my remainder. What did the question say? Oh, find the value of k which makes this remainder 0. So now we're at the very last part. We could just say, so I've done all this stuff and I've ended up with some number, and it would be nice if that remainder were equal to 0. So I'm just going to take all of this stuff right here, 7k minus, can I erase the top part here?
Yeah.
Okay, yeah, I want a bit more room. So I'm going to say, all right, that remainder is 7k minus 2 times all this stuff, which is 3 plus 2 times, man, this is ugly, k plus 2. Checking, yes, that is my remainder. That remainder needs to equal 0. So let's just knock this out. Well, it looks like I have k's. If I could group these k's together and get everybody else on the other side, I could solve this equation, right? Because I'm solving for one variable, one equation, it should be solvable. So it looks like I'm going to just go ahead and multiply this whole thing out. Why don't you do that too? You do that right now, I'll do it, and we'll reconvene in a minute and see if we get the same thing. Okay. That's what I get there. I'm going to keep multiplying until I have no parentheses left. You ready?
Mm-hmm.
Are you here? Did you get that?
Mm-hmm.
Okay, cool. So now I'm seeing, okay, if I could get all the k's on one side and everybody else on the other side, I'm good to go. So I'm going to take my 8 and my 6 over to this side. My 7 and my 4 k's give me a total of, I guess, positive 3k. Yep. And then 8 plus 6 is 14, 1, 4, yeah. Something like that. Finally, I can get k by itself by dividing both sides by 3. And I believe that is what the answer in the back of the book is. 14.
There is no answer at the back of the book. I don't. Oh wait, yes it is.
Yeah, for 31, I think. Like, did I make that up? Because I swear I looked it up. Like, where did that come from? Yeah.
Yeah.
Yeah, okay. And so now let's just kind of put this back in context. What this question is saying is that if our original thing, if our original polynomial were x to the third minus 14/3 x squared plus 3x plus 7 times 14/3, which we could rewrite if we were so inclined. If we had this to begin with, and we took it and divided it by the x minus 2, we would have a polynomial, some polynomial, ax squared plus bx plus c, where there is no remainder. It would be just a pure polynomial. That was the problem. Weird stuff pops up like this, where it's like, man, if I have some play, I could change a couple numbers in this equation, and it would make my life really easy if I could get this so that there were no remainder, because having a remainder means now I have something over an x, which is really, really bad usually for things that you want to do. If I could get this thing and manipulate it in such a way that I could get no remainder, oh man, that would make my life really easy. And so this is that type of thing that you're doing. It's like, well, I have some room to play here and I have some room to play here. If I can manipulate this thing so that I don't get a remainder, I'd be good. But we can in this case. It looks like we can if you did this. And if you want, have at it. Go actually do this division and you'd see that, yeah, you end up with a remainder of 0.
Okay. So
that's what this one's all about. It's a challenge problem. It's hard. It was a very hard problem. And yeah, that's why I assigned it. 32 is the same type of thing. Only in the end, you're going to have some equation involving k, and you want to set that guy equal to 7. And then you just solve for whatever you solve for k. And that's the idea.
Okay.
So no need to redo this one or anything like that. But I would like to see your work for 32. So you feel good to plug along and try 32?
Yes.
Cool. Okay. Any other questions on the stuff?
I don't think so.
Okay. Then I just want to briefly go over some tips and stuff. I don't want to introduce anything new today, especially since now we're going to be on Christmas break, and any homework you do or anything is just going to be long gone by the time, like it'll be way out of your mind. So, and I don't want to cover anything new without giving you homework either. So that just helps to reinforce everything. So what I'd like to do today is just to go over some general, what we've learned thus far with rational polynomials. So let's do this. In general, and I'm going to write something very general here. We have a polynomial, and that's the end, all the way down to a1x plus a 0. Once I get this written down, I'm going to describe what we're about to talk about. E to the m, x to the m, all the way down to b to the 1, x plus b0. What I'm going to do is we're going to have 4 different cases of types of things to do. The first type of thing is you have a polynomial divided by a polynomial. And in every case, I'm going to say, when you see that, what should immediately go through your head in order to turn this into a problem that is, or to turn this into an expression that we could make sense of. And so in the first case, and I'm just really reviewing everything, but I want to give it to you all in one nice chunk. So when we have some polynomial over another polynomial, the thing we do is we take this, we first factor it. Any way we can to get an expression like this. Okay, buddy. Then we cancel out anything that we could cancel out to give us a simpler expression. Like I said, I'm not giving you any new information here. This is just a review of what we've done thus far. Given a polynomial divided by a polynomial, we factor it down, and then we cancel anything out that is redundant, right? Like, for instance, if this were x plus 2, x plus 1, and x minus 3, and this were over x plus 7 and x plus 2, we would say, oh, hey, I just factored this guy down. The x plus 2 cancels with the x plus 2. So I could rewrite this as a simpler polynomial, which would be x plus 1 times x minus 3 all over x plus 7. And now I have something simpler to deal with than the beast that I started off with. Right? No news there, right? That's what we do. That's the idea, right? So whenever we have a rational polynomial, this is the goal. And given a polynomial of this form, one polynomial divided by another polynomial, this is what we do. So now we have a couple variations on this theme. Now, what I'm about to write some, it's going to look complicated, but I'm about to simplify it a lot. If we have a polynomial, a to the n, x to the n plus a to the 1x plus a0 over another polynomial, b to the m, x to the m, plus all the way down to b to the 1x plus b0 plus, oh man, this is getting ugly. And in fact, I'm about to simplify this a lot, but we have some kind of c to the l, x to the l, plus all the way down to c to the 1x, c0, and some d to the r, x to the r. I'm doing this with all these different letters to just kind of say, like, to try to make this as general as possible, to say, like, these don't all need to be to the same power. This could be an x to the third. This could be an x to the fifth. That could be an x to the first. That could be an x to the seventh or whatever. No matter what, you have this picture, right? The previous picture was some polynomial divided by a polynomial. And what we do is we factor it and cancel to try to simplify. In this case, you have a fraction of polynomials plus a fraction of polynomials. And what I'm going to do from now on for everything else that I'm about to write is I'm just going to write this simply as some polynomial over another polynomial. And we'll just know that that's not a constant number, that that's a full-on polynomial like that. That's a full-on polynomial. So all of that work just to say I'm simplifying this so that I don't have to write this out every time. But this is the picture. You see something like this, we're just going to simplify it like this in our heads and say, okay, well, if I see something like that, let me go ahead and just copy that down. I have some polynomial over a polynomial, some polynomial over another polynomial. What we want to do, the goal is to turn this thing into this thing, right? I want to rewrite this as one polynomial divided by another polynomial so that we could factor them down, cancel things out, and now we're in this as simple as we could get. Okay, so in this case, what we do, I'm going to put it in parentheses, factor, because usually life is much easier if you've taken a polynomial and factored it first. It's not necessary to do that, but that's usually our first step is we factor, and then we get a common denominator to add or subtract. And of course, this could be a subtraction too. This could be plus or minus the fraction, two fractions, that's fine. We get a common denominator. And in this case, what would my common denominator be? What's this denominator?
D.
What's this denominator?
D.
And so what am I missing over here?
A D.
A D. What am I missing over here?
A B.
A B, right? So in symbols, right, this is really straightforward. It's like the only thing I'm missing over here is that thing right there. And so we go D on top, D on the bottom. What did you tell me I was missing over here? What's missing in the down here?
A B.
A B. And so we multiply the top and the bottom by B.
Mm-hmm.
Now we have a common denominator. And I'm just going to rewrite that as BD. And then we have AD on the top, plus or minus CB. And now we're back here we have one polynomial in the numerator, one polynomial in the denominator. And if you've done this well, it should probably already be factored out. And so maybe we end up like in that situation where we were with problem 28, right? Where it's like we had something like this. And in the numerator, we had it was like a 1 plus x and a 1 plus h minus x times 1 plus x plus h. And that is kind of like this situation right here where we were like, well, hold up. Is there anything I could factor out and cancel? Well, no. Okay, so then maybe I need to multiply the stuff out. Then we multiply the stuff out. And once you've done that, now you're back into this scenario right here. And then we're just plugging and chugging, right? We're trying to cancel things in the numerator and denominator. Maybe they cancel, maybe they don't. Like in this case, everybody in the top canceled except for one h, which then we just divide it out. But that's the idea with that. One more thing I do want to say about this is I'm drawing a map for what to do. I'm not saying that whenever you see this, you plug this into this equation right here, because that's going to get really ugly. For instance, I just want to do this example real quick. If we had, say, x plus 1 over, let's go x plus 2 to the third power times x plus 3. And I want to go plus. I'm going to give myself a little bit of room here. I'm going to say plus. How about x minus 7 over x plus 2, x plus 3 to the...
Oh boy. Okay.
If we have something like this, right? Well, I'm not going to just take this thing, multiply it by that thing to get my new denominator. That's a bit overkill, right? It's like I could see that there's going to be a nice balance here. At most, I only need 4 of these in the denominator. And at most, I only need 3 of these in the denominator. And so I could say, well, same thing I'm doing here. It's like, what do I need to multiply on the top and the bottom to give me a common denominator? And I'm thinking, well, I'm going to need a total of x plus 2 to the third. And here I'm going to need an x plus 3 to the fourth, right? That should do it. And so how many more x plus 3s do I need over here?
3 of them.
3 of them. So I'm going to say, okay, if I multiply the top and the bottom by the amount that I need right there. So x plus 3 to the third. Over here, I'm deficient in x plus 2s. How many more x plus 2s do I need over here?
2 of them.
I need 2 of them. So I'm going to say, okay, x plus 2, I just need 2 of them. So I got to do that in the top and the bottom. Then this is going to be way simpler. It doesn't look very simple at all, right? But now we have a common denominator, and we can just count it up, right? We have 4x to the third, x plus 3s, 4x plus 3s. 3x plus 2s, and 2 and 1 make 3 total x plus 2s. And so now I do have a nice common denominator. But I didn't go through and just blindly say, well, everything that's in this denominator, I need to bring up over here, like in this fashion, and say everything that's over in this denominator, I need to bring up and do over here in that fashion to end up with something that would be ridiculously big. I just used the bare minimum of factors that I needed in order to get a common denominator. So that's a nice general principle right there. then that, and I've seen you do that in the homework, right? Like you don't go overkill when you're trying to find a common denominator. But I just really wanted to stress that point. Okay, so we're almost done. Oh man, we are not gonna go too far over today. That's a first. So polynomial over polynomial, factor it, cancel it, simplified form, that is what we're looking for. Oh no, we have a polynomial over polynomial plus or minus a polynomial over polynomial. No big deal. Just find the smallest common denominator you can. In other words, multiply the first thing until you have a nice common denominator. Multiply the second thing until you have a nice common denominator. Put them all together, and now you have an expression that is just like this. And then you go move along. Third case. You have fractions of polynomials. Oh no. Now what do we do? Let's say we have C, D, E over, let's say, B plus E, F, Q, Q, S. He hears me say letters and he just starts saying the ones he knows. It's so cute. Okay, so now we have fractions inside fractions. 9 times out of 10, it will be way easier to just kill the denominators than it would be to try to add those things together and then flip it all around. It's going to be much easier to just say, okay, you know what? If I could kill that guy and that guy, and that guy and that guy, I will be in this original situation. And so what we do is what I call kill denominators. There's no reason to find a common denominator and do all that stuff. I'm just going to say, well, I need to kill every denominator. And the way I'm going to do that is by writing 1 in a tricky way. I'm going to write something over itself, but that thing that I'm going to do will kill every single denominator. What do I need to kill that guy?
Multiply it by B.
It needs to be multiplied by B. Okay, so I'll do that in the denominator as well. What about, how do I kill that guy?
Multiply it by D.
Multiply it by D. Okay, so I need to do that in the bottom too. How do I kill that guy?
Multiply it by B.
Did I already do that?
Yep.
Yeah, so I don't need to go overkill. Again, we're not just we're gonna stop for a second and say, wait a minute. Did I already take care of that? Yeah, I already took care of that with that first multiplication by B. So I don't need to go above and beyond. If I did, okay, it's just gonna be uglier, but I've already done it. Now, what about that last denominator?
Multiply it by G.
G. So we need the G here and here. Okay, now let's see. You tell me, this would be a nice exercise. What happens? What do I get when this guy jumps over and hits that first fraction? What am I left with?
ADG.
ADG. What about in the second case, the second fraction?
CEG, I believe.
B, yeah, BG. Okay. Now what about in the bottom?
EDG.
EDG. And finally?
And then FBD.
FBD. Yep. And hey, look at that. One step and we're already in this situation. That's just a polynomial. That's just a polynomial, right? We are already, let's say this again. We took one step and we're already in this situation. That's the whole goal, right? Is to turn a problem we haven't seen before into a problem we've seen before. Just like this. We had this, a problem I haven't seen before. We turned it into a problem that we've seen before. That's what we're doing here. And I was able to do it with one step. I just did that. It's a lot easier than finding a common denominator, adding those together. Finding a common denominator, adding those together. Now I have two fractions. I multiply by the reciprocal and do my cancellation. And guess what? You would end up with the exact same thing. It's just I was able to do this all in one step. But in every case, we are trying to get to this thing right here, right? To our canceled one polynomial over one polynomial in its simplified form. When we have this, we factor it down to do this. When we have this, we get a common denominator, add them together, and then we are in this situation, we factor it down to get this. In this situation, we have fractions and fractions, so we kill the denominators, and now we have this, we factor it down and get it back into here. That's what we've done thus far. There's only one more thing that we're gonna do, which we're not gonna do any details, but to kind of finish up this picture, like from now on for the rest of your life, when you see something like this, you should immediately think, do this and this. When you see something like this, and remember, these represent polynomials, and remember, poor Justin sat here for like a whole minute writing out that first thing with a bunch of polynomials to really drive the point home that these are not letters, that we are representing full-on polynomials here. So when you see fraction of polynomials plus a fraction of polynomials, we should immediately think, I need a common denominator to get it back into this form right here. When you see polynomials as fractions inside a fraction, we kill the denominators to get us into this form so that we could do this. Finally, I'm going to go ahead and erase this. Are we good?
Yes.
Okay. Finally, the only thing that remains is what we're going to talk about next time, is when you have fractions of polynomials in an equation.
Mm-hmm.
And what that's going to look like is you have some polynomial over another polynomial. Well, maybe it's a sum of polynomials over another polynomial. And then you have A, B, C, D, E, and F. It's going to be almost exactly the same thing as we did in the last case, where we're just going to kill denominators. Because it will be way easier. Like you could see this and say, oh, I have a polynomial fraction and another polynomial. I better add those together and then do all this other. Well, it's kind of like in the last case. Like, yes, you could do that. I could have taken these two guys and added them together and then all of this stuff down here. But it's going to be way easier to say, well, you know, what would make my life a lot easier is if these fractions just didn't exist. And the nice thing about having an equation, so before what we had to do, and I do want to get into this, A, B, C, D, E, we had over B, and then we had an F over a G. What I did was, whatever I did to one side, I had to do to the other side of the divide sign, right? As I was figuring this stuff out. I said, man, a B would kill that guy. So I'm just going to multiply by B. But whatever I do to here, I got to do to here so that I don't change the overall fraction. And I said, oh, there's a D here. Whatever I do up here, got to do down here so that I don't change, and so on and so forth, right? Same thing here, only instead of with fractions, it's just, and you've already seen this a billion times, it's with sides of the equation. Whatever I do to one side of the equation, I got to do to the other side of the equation so that I don't change the overall equation. It's the same principle as this. It's just going to look slightly different. In this case, we're going to say, well, whatever's on one side and whatever's on the, I need to give myself some room, and whatever's on the other side. So on this side, we have A over B plus C over D. Here we have E over F. And I'm thinking, man, if that B wasn't there, that would make my life a lot easier. Wait a second, I could kill that B. And I could do that by multiplying by what?
B.
B. And so what do I have to do to this side in order to keep everything equal?
Multiply it by B.
Multiply it by B, right? And remember, it's the whole thing. I'm not just going in and multiplying this one guy by b and then multiplying that. I have to do the entire side of the equation, multiply it by b. What do I need to do to kill that guy?
Multiply it by d.
C. And so I do that to the other side because I have to keep the equation in balance. Now it's like, okay, if I do that, I will get rid of that guy. I'll get rid of that guy. I'll have a nice polynomial. How do I get rid of that guy?
Multiply it by f.
Right. And remember, we're imagining that these are like nice factored things. So I have like an x plus 1 over x plus 2 plus x minus 1 over x minus 3 squared. And then I have a, I don't know, how about 2x over x plus 1. It's the same principle. I could just say, well, if I multiply by this guy and that guy, he's gone, and that guy, he's gone. That's kind of the picture we have here, only instead of using actual factored terms, I just used letters. But this is the principle. This is where we're going next time. You're going to have equations like this. And it's like, oh no, don't worry about it. We're going to, as soon as you see something like that, step 1 is going to be kill denominators. And then that's pretty much it. Then usually we'll be able to solve these guys or at least get an expression that whatever. So, okay. That's it. That's all I got for you.